Today we are going to see buckling of column. So far we have seen so many structural members like bars which will take axial loads, and we have seen beams which can take transverse loads, and shaft which can take torsion loads. So today we are going to see column. So column is a structural member which can take axial compressive load. So buckling of column is a structural engineering phenomenon. Buckling of column is a structural engineering phenomenon that occurs when a column suddenly deflects laterally due to loss of stability. So there is a term called buckling load or critical load. So this is the load where the column cannot handle no more load and will become unstable. So in this experiment we are going to compute the critical buckling load both theoretically and experimentally. So this column is being used in many applications. For example, in aircraft structures, for example, we can take the stringers. The stringers will take axial compressive load, will lead to buckling, and also the landing gear struts also will subject to buckling. So that's why we need to understand the buckling of column. So it is used in many applications, especially aircraft structures. So now we are going to see the theoretical formula, how to compute the buckling load of a column using theoretical approach. So here we use Euler's column theory. So the critical buckling load is nothing but pi square E is nothing but the Young's modulus of the column, that is material property, and I is the moment of inertia against a geometrical parameter, and L is the equivalent length of the column. So why I have mentioned E here? Because the equivalent length will be changing with respect to the end conditions. For example, for pinned end condition, LE equal to L. Similarly, for fixed end condition, LE will be different. Similarly, for fixed free condition, my LE will be different. So like that, we have four different boundary conditions. So for four different end conditions, we have four different LE. In this experiment, we are going to use pinned end conditions. So for that, LE is equal to length of the column. Just I have shown the schematic of the column setup. So I have a long column having a length of L. This being subjected to axial compressive load. So, and also here I have shown the deformed shape of the column. So there is a load called critical load. If the load is applied beyond the critical point, then my column will lead to buckling and it will lead to collapse. So in engineering, we need to compute this critical buckling load for any column. Yeah. So far we have seen the theoretical formula to compute the buckling load of a column. So now we are going to see the experimental method to compute the buckling load of the column. So we have the hardware. In the hardware, we have to apply the load. Say I apply a load of 2 kg. So when I apply the load, you can see there will be a reflection. So that we are going to measure the reflection using an L gauge. So I may get 0.8 mm. And then you can take down the delta by P, that is 0.8 by 2 kg. You take down the value. So similarly, you can do it for several loads. So you can apply, you can increase the load to 4 kg, again 6 kg, like that. You can have so many loads. So now for each load you have reflection and also you have delta by P. Now to compute the experimental buckling load of a column, we are going to use a Southwell plot. So Southwell plot is nothing but we have made a graph between deflection and deflection by P. This is the axis title. So we are taking deflection as the x-axis and delta by P as y-axis. So already we have the delta values here and we have corresponding delta by P here. Just plot the values and you get a nice linear curve. So if you see the slope of the curve will give delta by P by delta. So this is the unit I have shown here, mm by kg by mm. So this is what you get. The slope you get in 1 by kg. So once you take inverse of the slope, you get the critical buckling load of the column. So the inverse of slope will give the critical buckling load. So and then you convert into Newton. So you get some value in Newton. So now we have computed the buckling load of the column experimentally using South Pole plot. Now you can compare this value with the theoretical formula. So already we have computed the theoretical buckling load. Now we can compare. So by this way, it is possible for us to compute the critical buckling load of column using both experimental method and the theoretical method.
We have a setup for testing buckling of columns. So this setup consists of a frame where we have the pin ends where you can place a column of various material. You can test it here. Now presently we have a column made of aluminum, and then we have weight hooks, thereby it acts at the center if you apply weight, and then you have a dial gauge which is pointing on to the column. When you apply load, this either bends in this direction or in this direction. So we will be able to measure deflection for the given applied load. So we keep applying loads here. For each and every load we apply, we will be measuring the deflection from the dial gauge. So we will be applying loads one by one. For example, 1 kg on both of these, and next 1 kg on both of these, and so on. So we will be able to measure deflection delta. Since we have measured the delta and P, to find the buckling load or P critical, we will be using Southwell plot, which is the deflection measured from this dial gauge divided by the applied loads versus the deflection. We will get a curve. From the slope we will be able to find the P critical or buckling load for this column. Assembling the setup, first we will place the column. Needs to be precisely placed because it's pin. Next we need to fix the dial gauge. The dial gauge is placed in the direction where it bends. Next we need to set 0. We can apply loads. And start measuring the deflection. We can go for 3 sets of loads or 5 sets of loads. We will be able to find the deflections against the applied load. To dismantle the setup, we will remove the weights. You can remove the dial gauge. Finally, the column.